From the very depths of what you are about to hear today, I might even venture to suggest that the bedrock, the very foundation of all true contemporary science, is, in essence, an undeniable form of magic. Imagine, if you will, a crisp December morning in the year 1998. The renowned cosmologist Max Tegmark, a figure whose intellectual curiosity often pushed against the boundaries of conventional thought, opens his email. The message that flashes across his screen sends a sudden, chilling jolt through him, a cold sweat pricking his skin. This email, a digital missive of considerable weight, arrived from one of the most eminent professors in his field, a senior figure whose pronouncements carried significant authority within the academic community. And within that message, a stark and rather unsettling admonition was delivered. The subject line itself was foreboding, a letter that was not easy to write. The body of the email began, "Dear Max, your insane articles are not serving you well. Primarily by submitting them to reputable journals and, unfortunately, succeeding in having them published, you are revealing their rather amusing side. I am the editor of a leading journal, and your article would never pass through my review process." The professor continued, his words dripping with a condescending concern. "This perhaps is not so crucial, except for the fact that colleagues consider these personal peculiarities of yours to be an ill omen for your future prospects. You must understand that if you do not completely separate this activity from your serious research, perhaps even ceasing it entirely, and if you do not relegate it to the pub or another similar venue, then you may very well jeopardize your entire career." The gravity of such a reprimand from a highly respected peer could have been crushing for a less determined individual. It was a direct challenge to Tegmark's intellectual path, a demand to conform to the perceived norms of serious scientific inquiry. When Tegmark, grappling with the weight of these words, forwarded this email to his father, the response was both succinct and profound, a quote echoing across centuries from the masterful poet Dante. "Follow your own road and let people say what they will." This ancient wisdom, a beacon of individual conviction, seemed to ignite an even stronger resolve within Tegmark, and indeed, Max Tegmark did precisely that. He followed his own path, unswayed by the criticisms and professional threats. Today, countless individuals, perhaps even you, the listener, have heard the name Max Tegmark hundreds of times. He stands as one of the world's most recognized and influential popularizers of science, a distinguished professor at the Massachusetts Institute of Technology, or MIT. He is the acclaimed author of several thought-provoking books that challenge our understanding of reality, a frequent participant in a myriad of educational broadcasts and documentaries, and so much more. His contributions span from theoretical physics to the ethics of artificial intelligence, a testament to his expansive and fearless intellect. So the question naturally arises, what exactly could he have written that so profoundly angered the author of that cautionary letter? What radical ideas in that professor's authoritative opinion should have utterly destroyed Tegmark's promising career? The answer, in its essence, is remarkably straightforward. Tegmark was simply too overtly expressive, too unreserved in articulating his views regarding what, from his unique perspective, our universe truly is. And if you find yourself asking, well, what exactly is it? Then you have arrived at the very heart of today's exploration. This is precisely what we shall delve into during this expansive monologue. Prepare to have your preconceived notions about reality gently, yet firmly, stretched and reimagined. Let us journey now to another remarkable account, recounted by the renowned neurologist and neuropsychologist Oliver Sacks. In his internationally best-selling work, The Man Who Mistook His Wife for a Hat. Sachs meticulously details 24 extraordinary case histories of individuals living with various neurological and psychological disorders. Each narrative is drawn directly from his rich and extensive clinical practice, offering a rare glimpse into the complex landscape of the human mind. Among these many captivating stories, there is one that stands out with particular vividness, a narrative so utterly astonishing that, were it not for the unimpeachable authority and integrity of Oliver Sacks himself, I would find it almost impossible to believe its veracity. This particular episode unfolded in the year 1966, a time when Oliver Sacks first encountered a pair of 20-year-old twins named John and Michael. These brothers had been subjected to a bewildering array of diagnoses throughout their young lives, labels ranging from psychosis and autism to severe intellectual disability. Over time, the majority of the physicians who had observed them eventually converged on a consensus, concluding that the twins were what are often referred to as, quote, idiot savants. This term, while now considered outdated and potentially offensive, was used to describe individuals whose talents were perceived as being narrowly confined to remarkable feats of memory, such as an infinite capacity for recall or the ability to instantly calculate the precise day of the week for any given date, stretching far into the distant past or the remote future. Their unique cognitive abilities, while astounding in their specificity, were often seen as isolated islands of genius amidst a broader sea of perceived deficit. However, Oliver Sacks, with his characteristic empathy and profound intellectual humility, offered a strikingly different interpretation. He wrote, and I quote directly from his observations, "I believe, however, that an error occurred, most likely an inevitable one, given the overly simplistic approach of the initial researchers. They attempted to force the twins into the rigid frameworks of standard questions and tests, thereby reducing their entire psychology, their very character, their entire life, to an almost complete emptiness." Sacks continued, his words imbued with a deep sense of a missed opportunity. "I think that, in reality, the case of the twins is far more astonishing, far more complex, and far more illuminating than the conclusions drawn by any of these initial investigators would suggest. Without abandoning the idea of testing the twins and ceasing to treat them like experimental subjects, it was simply impossible to suspect the depths of their understanding. True comprehension demands not experiment but contact. One needed to approach them humanly, calmly, and without prejudice. One needed to open oneself to their particular reality, the natural and unique reality of their lives and their thought, their relationship with each other." He concluded, with a note of wistful profundity, "And when this was achieved, it became clear that one was dealing with fundamental forces of the universe, with a vast cosmic mystery, the unraveling of which eluded me throughout the 18 years of our acquaintance." So what precisely was the core of this mystery? I want to emphasize that throughout this segment, I will be providing numerous direct quotes from Oliver Sacks, ensuring that you understand I am not embellishing or adding details of my own imagination. It is undeniably true that a significant number of mathematical prodigies exist, individuals who possess their own unique, often idiosyncratic methods of memorization and calculation. However, the true enigma of the twins begins with a truly astonishing phenomenon, one that, in this context, seems to defy all conventional understanding. While computational abilities are typically the hallmark of all arithmetic geniuses and calculators, when these variabilities were rigorously tested in John and Michael, a surprising fact emerged. Their capacity for calculation proved to be astonishingly poor. This was entirely consistent with their measured intelligence quotient, which hovered around 60. They made frequent errors in addition and subtraction, and the concepts of multiplication and division remained utterly beyond their grasp. How can this be? calculators who cannot calculate, individuals who possess no mastery of elementary arithmetic yet somehow perform what appear to be complex computations. How is it possible to perform calculations without actually performing calculations? This, however, was merely the beginning of the unfolding wonder. One day, Sachs recounted he witnessed a small cardboard box of matchsticks tumble from their table, its contents scattering across the hospital floor. Simultaneously, in perfect unison, both twins exclaimed, "111!" Then, John, almost as if sharing a secret, suddenly whispered, 37. Michael immediately echoed this number. John then repeated it a third time, and then fell silent. It took Sachs a considerable moment to manually count the scattered matchsticks himself. Indeed, there were precisely 111. "How could you count them so quickly?" Sachs inquired, a mixture of bewilderment and curiosity in his voice. The twins responded, again in unison, with a phrase that would resonate deeply with Sachs for years to come. "We didn't count them. We just saw that there were 111. This moment, it is worth noting, is famously referenced in the screenplay for the film Rain Man, when the character based on a savant similarly perceives a large number of dropped objects instantly. 82, 246 total. The character states, demonstrating this same immediate, non-calculating perception. Sachs, still intrigued by the interaction with the twins, pressed further. "And why did you whisper 37 and repeat it 3 times?" The twins again responded as one, their voices a melodic chant. 37, 37, 37 to 111. "How did you calculate that?" Sachs asked, his curiosity now fully piqued. In response, he received only confused explanations, all ultimately reducible to the assertion that they had not calculated anything, they had simply seen. Sachs realized his reaction must have struck them as deeply peculiar, as if Kokoro's were the one who was blind to an obvious truth. John's gesture in particular conveyed a vivid sense of some immediately, directly perceived reality. Was it possible, Sachs pondered to himself, that they in some way directly discerned the characteristics of numbers, not as abstract attributes, but as concrete properties, accessible to the senses? Sachs tried, without success, to rationalize and explain what he had just witnessed, but eventually he put aside his attempts. He was left with a profound sense of an intellectual frontier he could not yet cross. Then, one day, as he moved through the hospital ward, Sachs stumbled upon the twins engaged in a truly peculiar activity. They were seated quietly in a corner, exchanging mysterious smiles, seemingly immersed in a state of pure, intellectual bliss. Sachs, moving stealthily, so as not to disturb their profound concentration, drew closer and began to observe. The twins were deeply engrossed in a unique, purely numerical conversation. One would utter a 6-digit number, and the other, with a nod of profound recognition, would take it in. Sachs described it as if the second twin was tasting the number, savoring its essence. Then, the second twin would respond with another 6-digit number, which his brother, in turn, accepted with evident satisfaction. The twins, Sachs mused, were like 2 seasoned wine connoisseurs, having discovered a rare and exquisite bouquet during a tasting, and were now describing its subtle notes and complex layers to each other. What exactly were they doing? Sachs, meticulously as ever, recorded all the numbers they exchanged, then returned home. There he plunged into his reference books, poring over tables of powers, factors, logarithms, and, crucially, prime numbers. And there, amidst the columns of figures, he discovered something extraordinary. All the 6-digit numbers the twins had been exchanging were, in fact, prime numbers. But what is a prime number, and what makes this so remarkable? A prime number is a natural number greater than one that has no positive divisors other than 1 and itself. For instance, the number 7. If you attempt to divide it by any other number apart from 7 or 1, the result will always be a fraction. Thus, 7, 11, 13, and so on are prime numbers. When we consider small numbers like these, it is relatively straightforward to determine whether a number is prime or not. But if I were to ask you about a number such as 22, 111, for example, it becomes significantly more challenging to immediately determine if it is prime. Yet, the twins, who were demonstrably incapable of any conventional calculation, were effortlessly exchanging 6-digit prime numbers with each other, deriving immense, visible pleasure from this seemingly abstract numerical play. The following day, Sachs returned to the hospital, this time armed with a table of prime numbers. Finding the twins engaged in the very same game, he decided to conduct an experiment. He quietly approached them and, with a sense of anticipation, uttered an 8-digit prime number. The twins turned towards him, freezing in a posture of deep concentration, mingled with a hint of doubt. The pause that followed was the longest Sachs had ever observed in them, lasting a full half-minute or even longer. Suddenly, both simultaneously broke into a broad smile, their faces alight with an inner joy. It was clear they had, through some breathtaking internal verification process, seen that Sachs's 8-digit number was indeed prime. This discovery filled them with profound delight, a double ecstasy. Sachs had, in effect, presented them with a new toy, a prime number of an order of magnitude they had never encountered before. Over time, the twins progressed to exchanging 12-digit and then even 20-digit prime numbers. Sachs, to his consternation, could no longer verify these numbers, as his tables were only calculated up to a maximum of 10 digits. In the 1960s, such verification could only be performed by the most powerful supercomputers of the era, and even for them, it was no easy task. Moreover, there is no direct method to calculate prime numbers of such immense magnitude, and yet, the twins were doing it. Sachs concluded that it was unlikely any conventional calculations were involved whatsoever. The twins, he wrote, like angels, have direct knowledge. They directly perceive the arithmetic universe, the boundless heavens of numbers. Do we have the right to call this a pathology? It was a question that challenged the very definition of abnormality, pushing the boundaries of what was considered humanly possible. Let us transition now to a different, yet equally profound concept, the multiverse, specifically what Max Tegmark categorizes as the first level. The question of whether extraterrestrial civilizations exist, whether we are alone in this vast cosmic expanse, elicits a remarkably simple and unequivocal answer from Tegmark: yes. They most certainly do exist. However, according to Tegmark's intricate calculations, the journey to the nearest such civilization would necessitate traversing an unimaginable distance, a minimum of 1 billion kilometers. And, with roughly the same probability, these alien beings could be 1 billion times further still. While perhaps not the most practically useful calculation for interstellar travel, the crucial takeaway is that, with an almost certainty, they are out there. And here is precisely why this conclusion holds such weight. Consider for a moment the remarkable life of Maria Brañas Morera. As of the current moment, she holds the official distinction of being the oldest validated living person on the planet. She was born on March 4, 1907. During her formative years, when she attended school, she inhabited a world utterly different from our own, a universe confined by the limits of human knowledge at that time. In her lessons, she was likely taught that the entire cosmos consisted solely of our solar system, a relatively small collection of planets orbiting a single star, surrounded by a diffuse cloud of other stars. Yet within the span of her single extraordinary life, humanity's understanding of the sheer scale of the universe expanded so dramatically that the universe as Maria knew it in her school days became merely one speck within an incomprehensible multitude, one of several 100 billion other universes, which we now recognize and refer to as galaxies. Throughout the recorded history of humankind, such a radical expansion of our horizons has occurred repeatedly. Today we comprehend that space, at the very least, exceeds the greatest distances known to ancient hunter-gatherers by a factor of 1 billion times. But this staggering scale is just the beginning. Max Tegmark posits that, according to the most widely accepted cosmological model currently, the theory of inflation, space is not merely immense, it is, in fact, truly infinite. In his own words, the theory of eternal inflation is consistent with all modern observational data and serves as the foundation for most calculations and models presented at cosmological conferences. So what does this infinitely vast and, crucially, relatively homogeneously filled cosmos imply for the existence of extraterrestrials? Simply put, if space is infinite and filled with matter distributed more or less uniformly, then it necessarily follows that there must be an infinite number of alien life forms, not just life forms similar to our own, but forms of existence so utterly beyond our current comprehension that we cannot even begin to imagine them. In an infinite cosmos, everything that is not forbidden by the laws of physics must, by definition, exist somewhere. What might these unimaginable forms take? Perhaps a cosmic serpent, stretching across light years, devouring entire stellar nurseries for sustenance? In an infinite cosmos, the existence of such a creature is not merely a theoretical possibility, but a statistical certainty. Literally, everything is out there. Our universe, a realm of endless expansion, is an incredibly strange place. For example, if the fundamental laws of physics permit the existence of some form of life that consumes entire planets, then such monstrous entities are guaranteed to exist somewhere in some distant corner of this boundless expanse. Of course, we are inherently limited in what we can perceive. Due to the finite speed of light and the ongoing expansion of the universe, we reside at the center of a cosmic bubble, approximately 93 billion light-years in diameter. Beyond this observable horizon, the cosmos continues its endless stretch, but its contents remain forever hidden from our direct observation. Max Tegmark is widely recognized not only for his profound contributions as an astrophysicist, but also as the visionary founder of the Future of Life Institute. The primary mission of this institute is to steer the development of advanced artificial intelligence toward outcomes that benefit humanity, while simultaneously mitigating the myriad existential risks associated with its rapid advancement. Tegmark experienced a renewed wave of popularity following the 2017 publication of his influential popular science book, Life 3.0. In this work, he meticulously explores the far-reaching societal implications of integrating artificial intelligence that could potentially reach or even surpass human-level intelligence. For instance, he discusses the potential for a phenomenon he terms technological unemployment in the short term, a scenario where AI-driven automation could displace large segments of the human workforce. Consider this fascinating thought experiment. Imagine a miniature, toy universe, a simplified model where there are only 4 distinct locations for identical particles to occupy. In such a constrained toy universe, there could only be a finite number of possible combinations of matter, specifically 16 unique configurations. Now, extend this concept. Imagine that surrounding this initial toy universe, there are countless other, identical toy universes. The question then becomes, how frequently would the combinations of these toy universes repeat themselves? The answer is strikingly simple. On average, we would only need to inspect about 16 neighboring toy universes before encountering an exact duplicate. Now let us scale this profound concept to our actual, observable universe. Naturally, within our universe, the number of possible configurations of matter is far, far greater than a mere 16. However, these configurations, despite their vastness, are still fundamentally finite. Tegmark suggests that, according to a remarkably conservative estimate, there are no more than 10 to the power of 10 to the power of 118 ways in which our observable universe could be arranged. This is an almost inconceivably immense number. To truly grasp its scale, envision a number that begins with a 1, followed by 10 to the power of 118 zeros. This number is so astronomically vast that if you were to transform all the matter in the entire observable universe into ink, you would still not have enough to fully write it down. And yet, despite its monumental scale, this number is utterly negligible, infinitesimally small, when compared to the concept of true infinity. What does this profound disparity imply? It means that if you were to gaze out into the night sky in any direction, then at a distance approximately 10 to the power of 10 to the power of 118 diameters of the observable universe away from you, at that precise moment, an absolute identical copy of yourself would be looking back. This doppelganger would have lived precisely the same life, thought precisely the same thoughts, and performed every single action exactly as you have, right up to this very instant. Furthermore, this twin of yours would reside on an identical planet, within an identical solar system, within an identical galaxy, and within an identical observable universe. The entire history of their observable universe would be a complete and perfect replica of the history of our own observable universe. Thus, in an infinite universe, there exists an infinite number of these bubbles, each approximately 93 billion light-years in diameter, and each of these bubbles is utterly identical to our own. It requires little stretch of the imagination to understand that there must also be an infinite number of these bubbles where histories differ, whether slightly or dramatically, from our own. According to Max Tegmark, these are the parallel universes of the first level. As the eminent theoretical physicist and Nobel laureate Steven Weinberg once eloquently put it, it frequently happens in physics that the mistake is not that we take our theories too seriously, but that we do not take them seriously enough. Indeed, today we delve into some truly strange and expansive ideas. Some might question the purpose of contemplating such profoundly metaphysical concepts. Yet Tegmark reminds us that the boundary between what we categorize as physics and what we deem metaphysics is extraordinarily fluid and constantly shifting. Consider, for example, our understanding of the Earth's shape. Today, we unequivocally know that the Earth is approximately a sphere, but there was a time, not so long ago in the grand scheme of human history, when this was considered a purely metaphysical hypothesis, a speculative idea debated by philosophers and seafarers. Or think of the Earth's magnetic field, an invisible force that guides compasses and protects our planet from harmful solar radiation. We cannot directly perceive it with our senses, yet its reality is undeniable. Is this not, in its essence, a form of metaphysics made manifest? What about the phenomenon of time dilation, where time itself is observed to slow down at very high speeds, a prediction of Einstein's theories that has been rigorously confirmed? or particles that seem to exist in two places simultaneously, defying our classical intuition? The curvature of space-time, the very fabric of the cosmos warped by massive objects, and those enigmatic celestial bodies, black holes, regions of space-time where gravity is so strong that nothing, not even light, can escape. All of these, once relegated to the realm of metaphysical speculation to the wild imaginings of thinkers, are today established, incontrovertible facts of the physical world. This illustrates a crucial point. The line separating physics from metaphysics is not defined by the perceived madness or sheer audacity of a theory, as one might instinctively assume. Rather, this boundary is determined solely by the principled possibility of a theory's experimental verification. And even this criterion, it must be acknowledged, is not universally accepted among all physicists. It is becoming increasingly evident that theories grounded in modern physics can, in fact, be remarkably predictive, empirically verifiable, and, crucially, falsifiable. Max Tegmark, with his expansive view, suggests there are no fewer than 4 distinct levels of parallel universes. And for me, personally, the most compelling question is not whether the multiverse exists, for the existence of its first level, as we've discussed, hardly seems to be in doubt. Rather, the more profound inquiry is how many levels truly lie nested within it. But hold on, you might interject. We cannot possibly conduct an experiment to verify that space extends infinitely beyond the bounds of our observable universe. Tegmark counters this by explaining that we don't necessarily need to directly observe it. The parallel universes formed by infinite space, and indeed all the other types of parallel universes we will explore today, are not mere theories in themselves. Instead, they are asterisk predictions arising from certain highly successful theories. Allow me to elucidate this concept using a tangible example. Einstein's theory of general relativity, for instance, provides incredibly precise predictions regarding the orbital motion of the planet Mercury. Physicists are able to test this. They do test it, and they find that the theory's predictions align with observations to an astonishing degree of accuracy, often pushing the very limits of instrumental measurement. Furthermore, the theory also predicts that rays of light will alter their trajectory when passing near massive objects, a consequence of the curvature of space-time itself. This profound prediction was experimentally confirmed by Sir Arthur Eddington during a solar eclipse in 1919, an event that dramatically altered our understanding of the cosmos. Gravitational time dilation, the slowing of time in stronger gravitational fields, is another experimentally confirmed fact now routinely incorporated into technologies like GPS. However, general relativity also predicts phenomena that we will likely never be able to experimentally verify. For instance, to a certain degree, it describes the properties of space within time's black holes. How would you ever definitively check what lies inside? While you could, theoretically, embark on a perilous journey into a black hole, transmitting your observations back for publication in a scientific journal would, unfortunately, prove to be an insurmountable challenge. And yet, despite this practical impossibility, scientists take all of the theory's predictions about the interiors of black holes very seriously. No one, not a single reputable physicist, would deem these predictions unscientific, precisely because the theory's other predictions work with such astounding, even terrifying accuracy. Tegmark elaborates on this point, writing, "An important feature of physical theories is that if you like one of them, you have to buy it in its complete configuration. You cannot say, I like how general relativity explains Mercury's orbit, but I don't like black holes, so I want to do without them. You cannot buy general relativity without black holes. General relativity, he explains, is a rigid mathematical construct that does not permit selective modifications. You are compelled to either accept all its predictions or you must, from scratch, invent an entirely new mathematical theory that simultaneously agrees with all the successful predictions of general relativity and predicts that black holes do not exist. This, Tegmark notes, has proven to be an extraordinarily difficult task, and all such attempts to date have ended in failure. And it is by this very same principle that the theory of inflation, a cornerstone of modern cosmology, possesses its own set of rigorously verified predictions. It is an exceedingly successful theory, therefore we must take seriously all its predictions, even those that appear, at first glance, to be untestable. This includes, unequivocally, the concept of an infinite cosmos and the existence of parallel universes. Tegmark concludes, even those of my colleagues who dislike the idea of the multiverse are now inclined to admit that the main arguments in its favor make sense. In general, the criticism has shifted from, "This doesn't make sense and I hate it," to "I hate it." This humorous observation underscores the growing, albeit sometimes grudging, acceptance of these once radical ideas within the scientific community. Physics, it turns out, reveals a reality far more intricate and sophisticated than we could ever have possibly imagined with our mere senses. Is this surprising? Perhaps not, when we consider our evolutionary heritage. Evolution, after all, endowed us with intuition only for those aspects of physics that held direct relevance for the survival of our distant ancestors. This is why we are genuinely shocked when, at extremely low temperatures, liquid helium begins to flow upwards, defying the familiar pull of gravity. It is an alien behavior that clashes with our deeply ingrained everyday experience. Yet, there is something else, something equally astounding, that surprisingly no one ever seems to find astonishing, something you likely never pay attention to, something you probably didn't notice even this time around. Consider again, general relativity is a rigid mathematical construct. The theory's predictions work with astounding accuracy. What is it that strikes no one as peculiar? How was the greatest theory in the history of humankind discovered? Did Einstein gaze through a telescope and simply see his theory emerge? No. Did he conduct elaborate measurements and experiments to unlock its secrets? Again, no. Instead of performing any experiments or observations, he spent 9 years secluded in his home, meticulously filling sheets of paper with what, to most people on the planet, would appear as nothing more than strange runes and mystical pentagrams. 9 years! And we, in our modern parlance, refer to this as mathematics, doing so with an air of understanding, as if we truly comprehend what we are talking about. Perhaps it will surprise some, but the most knowledgeable individuals in mathematics, the mathematicians themselves, openly admit that, by and large, they have no clear idea what mathematics truly is. As the distinguished English philosopher Sir Michael Dummett once remarked, the two most abstract academic disciplines, mathematics and philosophy, provoke the same bewilderment. What exactly are they about? And this bewilderment, he added, is not merely due to a lack of general knowledge. Even specialists in these respective fields find it profoundly difficult to answer this question definitively. But we will ponder that deeper philosophical mystery later. For now, I am attempting to draw your attention to something else entirely. Let us consider gravity itself. Have you ever truly observed the peculiar strangeness in the way objects fall under the influence of this fundamental force? Imagine we have a falling ball. It drops, and in the first second it covers a certain segment of distance. Now, what length of distance do you imagine it will cover in the very next second? I won't keep you in suspense. In the subsequent second, the ball will travel 3 times that initial distance. In the third second, it will cover times 5 times the initial distance. In the fourth, times 7 times. In the fifth, const 9 times, and so on, continuing with 11, and then ever-increasing odd numbers. Observe this sequence once more. What, in your estimation, is the strangeness embedded within this progression? If you pay close attention, you will not detect a single even number. The fall of any object, under the uniform pull of gravity, unfolds as a precise sequence of odd numbers. This remarkable pattern was first discovered by Galileo. You could measure these segments not just once per second, but perhaps once every 5.5 seconds or even once every 2 minutes. The specific time interval is irrelevant. Regardless of the temporal unit you choose, you will invariably obtain this exact sequence. The ball falls as if the universe itself possesses an innate, precise understanding of what constitutes an odd number and, by extension, an even number. This is a rigorous mathematical law, and like any true law of nature, it admits no exceptions. It is a law which, for some inexplicable reason, is intricately woven into the very fabric of the cosmos. Our expectation, perhaps, would be that a ball might fall slightly differently each time, exhibiting some degree of random variation. Even Einstein himself found this profound mathematical order deeply perplexing. I recall his words to the mathematician Maurice Sullivan. "You find it astonishing that I speak of the comprehensibility of the world as a miracle or an eternal mystery. Well then, a priori, one should expect a chaotic world, one that is impossible to grasp through thought. Yet, in such a chaotic world, the brain, it seems, simply could not have evolved. For instance, according to the American neurobiologist Dean Buonomano, if one were to formulate the entire essence of the brain's function in 2 words, the best definition might perhaps be future prediction. The brain, in its incessant activity, constantly performs complex mathematical calculations. You, for example, might not consciously understand why, when presented with a pair of faces, one appears distinctly more attractive to you than the other. But your brain knows. It has already processed all the data, made all the intricate computations. The calculations involved in determining facial beauty are so astonishingly complex that, in the English-speaking digital sphere, there exists an entire YouTube channel dedicated solely to researching which faces the human brain finds attractive, and it already boasts over 500 videos. This means, quite literally, that facial attractiveness is fundamentally about specific numbers, percentages, ratios, and proportions, details of which you may have absolutely no conscious awareness, but which your brain has always intrinsically known. It carries out these mathematical operations and delivers a prediction. Yes, this individual would likely produce robust offspring. We, in our human experience, simply label this sensation as attractiveness or beauty. Naturally, this extends beyond just the face. Consider, for example, how many individuals meticulously train in fitness establishments, performing strenuous exercises with barbells to enhance the volume of their gluteal muscles. However, it appears that the asterisk volume self may not be as crucial as the precise curvature of the lumbar spine. Men, across cultures, perceive the most attractive angle of lumbar curvature to be approximately 45.5 degrees. You might find yourself asking, why precisely these specific numbers and ratios? While some of these can be explained through evolutionary biology, the world simultaneously abounds with a multitude of precise numbers whose origins remain utterly perplexing. Consider the enigmatic number pi, for instance, the ratio of a circle's circumference to its diameter. It appears in the most disparate areas of physics, from celestial mechanics to quantum field theory. Why is its value precisely what it is? While the number pi has by now become somewhat familiar to many, there are other, equally mysterious numerical constants that resonate throughout the universe. Take, for example, the fascinating tale of Mitchell Feigenbaum. In 1975, while working at Los Alamos National Laboratory, Feigenbaum was provided with a sophisticated, state-of-the-art pocket calculator, an HP 65. This marvel of engineering, adjusted for inflation, would have cost nearly $5,000 in today's money. Feigenbaum, captivated by his new technological toy, began to explore the behavior of a simple mathematical function on it. He discovered that a sequence of numbers generated by his calculations continually converged closer and closer to a particular, definite value. This value was approximately 4.6692016. As Feigenbaum delved into other, seemingly unrelated equations, he was astonished to find that this same mysterious number appeared there as well. He concluded that he had uncovered some universal regularity, a profound constant that somehow marked the transition from order to chaos, yet he could not find a theoretical explanation for its existence. Initially, physicists greeted this discovery with considerable skepticism. Why, they questioned, should the exact same number characterize the behavior of wildly different systems? Indeed, Feigenbaum's first paper on the subject underwent a grueling 6-month peer review process, after which it was ultimately rejected. However, very soon experimental evidence began to emerge, showing that a vast array of natural phenomena behaved precisely in accordance with Feigenbaum's predictions. For instance, his constant accurately predicts the transition from an ordered, laminar flow of a liquid or gas to the turbulent, unpredictable flow. But beyond that, this number arises even when measuring the population dynamics of living organisms, the reaction of the eye to flickering light, the fibrillation of the heart, and even the behavior of water droplets falling from a faulty faucet. Today, this profound and ubiquitous number is known as Feigenbaum's constant. The theoretical physicist and Nobel laureate Eugene Wigner once famously articulated a phrase that has since become widely recognized. The unreasonable effectiveness of mathematics in the natural sciences is something bordering on the mystical, and there is no rational explanation for it. This statement encapsulates a deep, persistent wonder that resides at the heart of scientific inquiry. Have you ever truly contemplated what you are doing when you listen to music? What, fundamentally, is the act of listening to music, and why do we derive such profound pleasure from it? In school, we were undoubtedly taught about Pythagoras' theorem and the legendary figure of Pythagoras himself. But what we were decidedly told in school was that Pythagoras was, in fact, the founder of a highly structured, almost totalitarian cult dedicated to his own person. Its adherents literally worshipped numbers, believing that mathematics was, in essence, the very embodiment of God. Their guiding motto was the powerful declaration, "All is number." To truly understand the gravity of their convictions, consider this. When one of his students, Hippasus, mathematically proved that not all things could be expressed as whole numbers, thereby discovering irrational numbers, he was, sometime later, found drowned. It is speculated that this radical challenge to their numerical dogma may have played a role in his demise. Pythagoras himself made a profound discovery. Music, he found, is inherently mathematical. He observed that the most pleasing sounds to the human ear corresponded to specific, simple ratios of vibrating strings. These ratios were primarily 2:1, an octave, 3:2, a perfect fifth, and 4:3, a perfect fourth. These specific tonal combinations became the fundamental bedrock of classical music, the majority of folk music, and indeed, much of pop and rock music as we know it today. Thus, Pythagoras uncovered a deep truth, the harmony of sound that we perceive, that resonates so profoundly within us, reflects precise mathematical relationships that exist in a seemingly entirely different realm, the world of pure numbers. I genuinely do not know how many times today variations of this question will arise, but how is such a phenomenon even possible? The German mathematician Gottfried Leibniz, contemplating this very mystery, wrote, "Music is nothing but an unconscious exercise in arithmetic, a hidden profundity of the soul in its unthinking activity, which knows that numbers are numbers, but does not know that it is counting." Arthur Schopenhauer, with his characteristic philosophical depth, believed that all of existence is an embodiment of a universal will, and that music is its most direct and unmediated manifestation. Music, he argued, in contrast to the other arts, is the direct imprint of the will itself. That is why the effect of music is so much more powerful and profound than the effect of the other arts, for the latter speak only of the shadow, while music speaks of the essence. He further expounded on the profound truth of Leibniz's observation. Music is nothing other than a way of grasping directly, and in reality, those large numbers and numerical relationships that we can generally only know indirectly, in concepts. And here's an intriguing connection. Individuals with acquired or congenital savant syndrome, much like the twins I described at the outset of this monologue, often exhibit extraordinary abilities not only in mathematics but also in music. This confluence of talents compels us to ponder deeper implications. As Oliver Sacks observed, random numbers and indeed any arbitrary sequence brought no pleasure to the twins. In numbers, they actively sought meaning, conbers, mopple. Perhaps, in a similar vein, musicians, with their attuned sensibilities, seek harmony and profound structure within sounds. Sacks noted that even in the prime numbers that so captivated the twins, there exists a genuinely mystical, hidden pattern. This pattern was, quite by chance, discovered in 1963 by the mathematician Stanislaw Ulam, and it is something that even we, as ordinary individuals, can readily perceive. Ulam, finding himself subjected to a particularly long and exceptionally tedious lecture, attempted to amuse himself. He began to doodle on a piece of paper, drawing vertical and horizontal lines, intending to create a series of chess problems. Instead, almost instinctively, he started to number the cells. He placed the number 1 in the center, and then, moving outwards in a spiral pattern, he wrote 2, 3, and so on. As he proceeded, he automatically marked the prime numbers. To his utter astonishment, he observed that these prime numbers tended to align along certain diagonal lines, forming a distinct, harmonious pattern. Greatly surprised by this spontaneous discovery, Ulam returned from the lecture and, utilizing a computer, created a visualization of what 90 million prime numbers would look like when arranged in this spiraling manner. What he saw was truly breathtaking. This visual phenomenon is now famously known as the Ulam spiral. The profound question it poses is this: why do numbers that are divisible only by themselves and by 1, when arranged in this specific way, give rise to such unexpected beauty and order? This leads us to the multiverse of the second level. The esteemed physicist and cosmologist Alan Guth is credited with proposing the groundbreaking idea of cosmic inflation, a theory that, as we've already discussed, predicts the existence of the first-level multiverse. However, it turns out that the very same theory of inflation also predicts the existence of a second-level multiverse. This further elaboration of the inflationary paradigm was brilliantly demonstrated by Alan Guth himself, alongside other pioneering physicists such as Andrei Linde and Alexander Vilenkin. Guth, in a particularly insightful lecture delivered at the Massachusetts Institute of Technology, once noted that whenever we identify an object in nature, the scientific approach compels us to seek out the mechanism that brought that object into being. For instance, automobiles are manufactured in factories. Rabbits come into existence through the reproductive efforts of parent rabbits, and planetary systems are born from the gravitational collapse of colossal molecular clouds. By this logical extension, we must then infer that our entire universe was itself the product of a mechanism designed for creating universes. And here lies the crucial insight. Car factories, rabbit parents, and gigantic dust clouds invariably produce multiple instances of what they create. A universe containing only a single automobile, a solitary rabbit, or just one planetary system would strike us as profoundly unnatural, an anomaly defying all observed patterns. Therefore, by this very logic, the mechanism that birthed our universe must also have brought forth a multitude of others. The first-level multiverse, as we discussed, is essentially a single, infinitely expanding universe where, given enough space, everything eventually repeats itself. But the second-level multiverse represents a far more intriguing and complex structure. Consider this compelling piece of evidence. Observe the masses of the 9 fundamental fermion particles, which have been successfully measured. This array of numbers represents the masses relative to the electron's mass. And what is remarkably striking about these 9 numbers? They successfully pass a rigorous statistical test for randomness. In simpler terms, these numbers appear precisely as if someone had haphazardly thrown 9 darts at a dartboard, with no underlying pattern or discernible reason for their specific values. This observation, in itself, raises a multitude of profound questions. But let us delve deeper. Imagine you are tasked with precisely adjusting a circular dial that controls the density of dark energy, a mysterious repulsive force pervading the universe. You must exercise extreme caution. If you over-adjust, the dark energy will become too powerful, preventing the formation of stars and galaxies. However, if you under-adjust, the universe will rapidly collapse under its own gravitational pull, long before complex structures can emerge. You might inquire, what, then, is the permissible range for this adjustment? Physicists have calculated that the maximum conceivable value is approximately 10 to the power of 97 kilograms per cubic meter, at which point space would be filled with tiny black holes. Conversely, the minimum value is around 10 to the power of negative 97 kilograms per cubic meter. Given this colossal range, with what astonishing precision do you believe you would need to turn this hypothetical dial for our universe to even exist in a form hospitable to life? The answer is mind-boggling. The angle of rotation would need to be set with an accuracy exceeding 120 decimal places. No matter how many times you tried to rotate this dial, it would be almost impossible to land on the correct setting by pure chance. And yet some intricate, unseen mechanism clearly provided this incredibly precise service to our universe. Moreover, the universe is not governed by just one such dial. It possesses a myriad of these finely tuned parameters. Tegmark notes that the scientific community is gradually realizing that many of these cosmic dials are indeed exquisitely fine-tuned. For instance, if the strength of the electromagnetic force were to weaken by merely 4%, our sun would immediately explode. How can we possibly explain such an improbable cosmic alignment? There are, broadly, 3 main possibilities. The first is simply a chain of exceptionally fortunate coincidences. However, The scientific method, in its very essence, abhors unexplained coincidences. As Tegmark writes, to say that my theory requires an inexplicable coincidence to agree with observations is equivalent to saying, my theory is wrong. This option, therefore, is scientifically unsatisfactory. The second possibility is divine intervention, the notion that a higher power purposefully set these dials. While this offers a superficial explanation, it is not significantly better than the first, as it explains nothing about how or why, and itself raises a host of other, equally profound questions. It simply shifts the mystery rather than resolving it. The third, and scientifically more compelling, option is proposed by the theory of inflation. This theory posits the existence of a boundless space that is continuously expanding, essentially boiling with energy. Within this furiously expanding cosmic cauldron, like bubbles forming in boiling water, countless pockets of space spontaneously appear. Each of these bubbles is, in effect, a first-level multiverse, complete with its own infinite internal space. All these infinite bubbles taken together collectively form the second-level multiverse. If you find yourself pondering how an infinite space could possibly be contained within the finite volume of these bubbles, I would offer an even more mind-bending thought. To an external observer, all these individual universes might appear as formations smaller than an atom, perhaps resembling something like this: a black hole containing a subatomic universe, its internal space, nonetheless, infinite. Thus, what we conventionally refer to as the Big Bang was not the absolute beginning of everything, but rather an asterisk end, the cessation of inflation in our specific region of spacetime. In other regions, inflation typically continues eternally, constantly spawning new bubble universes. And it should come as no surprise that the vast majority of these second-level parallel universes are dead, barren, and devoid of life due to their unfortunate, randomly selected settings on the cosmic dials, rendering them inhospitable to any form of complexity. In discussing the second-level multiverse, Tegmark often invokes a statistical approach, highlighting its remarkable efficacy. He points out that the predictions derived from this framework align splendidly with observed data. And if we pause to truly consider this, it is, in its own way, profoundly absurd. How can randomness possess regularity? It sounds like a genuine oxymoron. But let us put aside the grand scale of the multiverse for a moment and consider this phenomenon at our everyday human level. A fascinating example comes from the Belgian mathematician Adolphe Quetelet, who, driven by an insatiable curiosity, decided to undertake a superscale research project. He meticulously collected thousands upon thousands of measurements of various human body parameters. For instance, he recorded the chest circumferences of 738 Scottish soldiers, the heights of 100,000 French conscripts, and so on. A rather eccentric individual, perhaps, but his dedication yielded profound insights. What he discovered was truly remarkable. When he graphically represented all these measurements, he consistently obtained a characteristic bell-shaped curve, which we now universally refer to as the normal distribution curve. The more data he gathered for any given parameter, the more perfectly defined and clear this curve became. For example, if you consider a parameter like human height, the absolute majority of individuals will fall within a similar average range, while extreme deviations will affect only a minority. Very short individuals on the left side of the graph and very tall ones on the right. Quetelet subsequently extended his work, constructing similar curves for what he termed moral traits, for which he could gather sufficient data. This included characteristics like marriage rates, propensities toward criminality, and intellectual abilities. To his profound astonishment, Quetelet found that all human characteristics, without exception, obeyed this same normal distribution. Time and again, the identical bell curve emerged. But what was truly astonishing was that Quetelet recognized in this curve a pattern already familiar to physicists since the mid-18th century, a curve known from astronomical observations. How could this be? How could astronomical, biological, and social processes be linked by some universal underlying law, especially given that social processes are often perceived as utterly chaotic? The very fact that the distribution of such diverse traits, from body weight to IQ scores, adheres to the same normal curve is, in itself, a testament to an underlying order. But it goes further. Even the distribution of average successful pitches in Major League Baseball, for instance, exhibits a more or less normal distribution, as do the returns of stock market indices composed of numerous individual funds. Moreover, if a distribution deviates significantly from the normal curve, it typically signals a need for thorough investigation. As the astrophysicist Mario Livio notes, for example, if the distribution of English language grades in a particular school differs from the normal, it suggests a need to check the grading rules adopted there. This universal pattern suggests a deep, hidden structure beneath seemingly random occurrences. And there is still more to this story. In 1906, the researcher Francis Galton, a cousin of Charles Darwin, and a frequent subject of discussion on these deep science explorations, conducted a significant observation at a rural fair. Fairgoers were offered a prize if they could accurately guess the precise weight of a slaughtered ox. The winner would be the one whose estimate was closest to the actual weight. A total of 787 people participated in the contest, a remarkably diverse group that included knowledgeable farmers, individuals who possessed a keen intuitive understanding of livestock, as well as those utterly removed from animal husbandry. Who won the prize is not important for our present discussion. What is truly significant is what Galton meticulously calculated after the fair. The average value of all 787 guesses came out to be 547.5 kilograms. How close, do you think, was this collective average to the actual weight of the ox? The astonishing answer: the error was less than 1%. Absolutely chaotic, disparate answers from participants who varied in every conceivable way, when aggregated, converged to a remarkably precise and specific result. This phenomenon has since been replicated numerous times across various fields. Galton, profoundly impressed by his findings, sent the results of his observation to the esteemed journal Nature, titling his letter Vox Populi, the voice of the people. Today, this remarkable effect is commonly referred to as the wisdom of the crowd. It is thanks to this very effect that, for example, democracies, despite their inherent complexities and potential for discord, often prove to be surprisingly robust and effective forms of societal organization. Historically, such a system, where decisions are made by a diverse populace, might have appeared suicidal, a recipe for chaos. The wisdom of the crowd is also the principle underpinning systems where the verdict of guilt or innocence in serious criminal cases is decided not by professional lawyers or judges, but by a jury, a panel of ordinary citizens selected through random sampling. Moreover, this collective intelligence forms the basis of various online services, such as the ubiquitous Wikipedia, where collective knowledge curation leads to robust information, or the online platform Kulu, launched in 2015 by a group of scientists and researchers. On Kulu, individuals can submit their predictions regarding future events, and the platform then displays the averaged result of all submissions. Many of the predictions generated by this collective wisdom have proven to be accurate with astonishing precision. These examples compel us to ask a profound question: can mathematical regularities truly permeate all of existence, from the largest cosmic structures to the most intricate human behaviors? Let us delve into another extraordinary story that further deepens this mystery. On January 31, 1913, Godfrey Harold Hardy, a brilliant Cambridge mathematician, received a package of documents. Accompanying these papers was a letter from the author, who humbly stated that he had achieved astonishing progress in mathematics and implored Hardy to publish his work if he deemed it valuable, explaining that he himself, due to his extreme poverty, was unable to afford publication. The package contained 11 pages filled with complex technical results spanning a wide array of mathematical domains. Most of the derivations represented mathematical theorems already known to Hardy. However, some of them were utterly new to him, and they profoundly disconcerted him. Hardy later recalled, "I had never seen anything in the least like them before. A single glance at these formulas was enough to convince me that only a mathematician of the highest caliber could have derived them. They had to be true, for if they were not, no one would have had the imagination to invent them." The mathematician of the highest caliber was a young man from India named Srinivasa Ramanujan. What made this even more astonishing was that Ramanujan possessed no formal mathematical education. He had never attended a university and had never interacted with serious mathematicians in his life. Hardy shared this astonishing discovery with his colleague and fellow mathematician John Littlewood. Both were unequivocally convinced they were dealing with a genius, an individual who, entirely on his own, had retraced a century-long journey of European mathematicians. As Hardy poignantly observed, before him lay an almost impossible task: a poor Hindu with no resources but his brains, pitted against the accumulated wisdom of Europe. Ultimately, Hardy exerted considerable effort and successfully arranged for Ramanujan to travel to Cambridge for collaborative work. Why do I recount this particular story? The profound problem lies in the fact that, to this day, no one truly understands the method by which Ramanujan derived his formulas. Hardy himself remarked that Ramanujan's conception of what constituted a mathematical proof was, to say the least, most vague. Ramanujan would spontaneously produce incredibly complex arithmetic theorems, the proof of which would require a modern computer. Often, these were transitions from one moment of profound insight to another, with no formal demonstration or logical steps in between. It seemed ridiculous, Hardy noted, to plague him with questions about how he had derived one or another known theorem, when he was showing me almost daily half a dozen formulas that were unquestionably new and very important. Ramanujan himself attributed his abilities to divine inspiration, claiming that the goddess Namagiri revealed formulas to him in his dreams. His notebooks, filled with concise summaries of his published and unpublished results, spanned 400 pages, forming 3 dense volumes. These were entirely composed of astonishingly powerful theorems, but contained no commentary and, crucially, no proofs whatsoever. And as if this were not enough, in 1976, by sheer serendipity, a box in the archives of Trinity College yielded a treasure trove, 130 pages of Ramanujan's notes from the final year of his life. These pages contained yet another 600 formulas, again presented without any proofs or derivations. Over the subsequent decades, almost all of these formulas would be rigorously proven to be correct. The mathematician Richard Askey, commenting on these notes, stated, "The work he did in that last, dying year is comparable to what a great mathematician might do in a lifetime. His achievements are incredible. If they were described in a novel, no one would simply believe it." Mathematicians Jonathan Borwein and Peter Borwein, reflecting on their arduous work to decipher this final notebook, wrote, "No known attempt at mathematical editing of such volume and complexity had ever been undertaken before." Mathematician Bruce Berndt observed, "The discovery of this manuscript caused about as much commotion in the mathematical world as would the discovery of Beethoven's 10th Symphony in the musical world. The physicist and mathematician Stephen Wolfram, in an article titled Ramanujan's Legacy, wrote, "Ramanujan's complex formulas hide behind them an incredibly impressive history. It's wonderfully impressive that he could derive them without computers or other modern tools. When I look at Ramanujan's results, many of them strike me as random facts of mathematics. Yet, work on his notes, especially in recent decades, shows that they are not random. Rather, it is increasingly found that they conform to deep mathematical laws." Theoretical physicist Freeman Dyson once simply stated, "He had some magical tricks we don't understand." I have provided so many quotes from renowned scientists precisely because it is the only way we, as ordinary mortals, can even begin to glimpse the sheer scale of Ramanujan's genius. There is, incidentally, an excellent film from 2015 about him, The Man Who Knew Infinity, which also helps one to empathize with his extraordinary journey. His notebooks were analyzed and studied for decades after his death, serving as a rich source of new mathematical ideas. But the most fantastic aspect, the one without which Ramanujan's story would lose its profound meaning in the context of our current discussion, is this. His formulas are today, quite unexpectedly, being used in string theory and for the study of black holes. When he lived, terms like string theory and black hole did not even exist. In some mysterious, almost magical way, by deriving his formulas, he provided answers to theoretical physics questions that no one had even posed yet. And this despite the fact that he had absolutely no connection to physics whatsoever, dedicating himself solely to pure mathematics. How can such a thing be possible? Galileo Galilei, in his profound wisdom, once declared, "Philosophy is written in that grand book, I mean the universe, which stands continually open to our gaze, but it cannot be understood unless one first learns to comprehend the language and interpret the characters in which it is written. It is written in mathematical language, and its characters are triangles, circles, and other geometric figures, without which it is humanly impossible to understand a single word of it. Without these, one is wandering about in a dark labyrinth." If we were to offer a simplistic, everyday explanation for the effectiveness of mathematics in the natural sciences, the reasoning might sound something like this. Well, humans observed the physical world and eventually grasped some properties of addition, subtraction, and so forth. For instance, it's clear that if you eat one apple out of 3, you'll have 2 left. Likewise, almost anyone, sooner or later, would conclude that space contains only 3 dimensions. From the perspective of such reasoning, it would seem unsurprising that mathematics and physics walk hand in hand, intimately connected. However, the fundamental flaw in this logic is that mathematics proves remarkably effective in areas so utterly removed from direct human perception as to be almost inconceivable. Consider Albert Einstein once more. Many mistakenly believe he received his Nobel Prize for his theory of relativity. But this is not the case. The Nobel Committee for a decade steadfastly rejected his candidacy, despite nominations from such titans of science as Lorentz, Planck, and Bohr. Why? Various factors are cited, chief among them the scarcity of experimental data to confirm his theories. I reiterate, all of his work, his entire intellectual endeavor, was complex mathematics, devoid of any practical experiments. So, on one hand, some members of the Nobel Committee struggled to comprehend the essence of his theories. On the other, they harbored significant skepticism regarding whether phenomena like time dilation and the curvature of spacetime were actually real, physically existing entities. It's difficult to fault them for their initial incredulity. This stalemate persisted until the incoming experimental data became simply impossible to ignore. But even then, paralyzed by indecision, the committee awarded Einstein the Nobel Prize not for the theory of relativity, but for what is widely considered his most modest achievement, his explanation of the photoelectric effect. So why does mathematics so accurately describe phenomena that humanity has never encountered throughout its entire history? Why, for example, is the inaccessible world of subatomic particles so perfectly described by mathematics, a tool that was, ironically, developed through the counting of everyday objects like apples? And why do the formulas of Ramanujan, a man who had absolutely no connection to physics, find profound application in the most cutting-edge physical concepts a century later? Why, ultimately, even Ramanujan's mentor, the very same Harold Hardy, who openly prided himself on his work containing nothing but pure mathematics and famously wrote in his celebrated book, A Mathematician's Apology, "I have never done anything useful. No discovery of mine has made, or is likely to make, directly or indirectly, for good or ill, the slightest difference to the amenity of the world." Why did even his formulas find real-world application, for example, in the Hardy-Weinberg law? Once more, how can such a thing be? This profound mystery brings us to the multiverse of the third level. Let us journey back in time to the chilling night of September 26, 1983. Near Moscow, within the confines of a command center for a nuclear early warning system, computers suddenly shrieked. The automated systems reported that intercontinental ballistic missiles had been launched from the territory of the United States of America. The level of reliability for these readings was categorized as maximum. For the duty officer, Lieutenant Colonel Stanislav Yevgrafovich Petrov, and the handful of other individuals in the command center at that precise moment, a single, terrifying thought flashed through their minds. World War III had begun. Petrov's heart hammered wildly in his chest, his breath catching in his throat. "I couldn't stand up from my chair," he later recounted. "My legs gave out." According to the strict military protocol, Petrov was absolutely obligated to report this attack up the chain of command, a sequence of orders that would inevitably have led to a retaliatory nuclear strike against the United States. "I had only a few minutes," he recalled, "to report the threat to the country's leadership." The incoming missiles were estimated to detonate on Soviet territory in a mere 30 minutes. The tens of thousands of nuclear bombs accumulated over decades of the arms race, a terrifying arsenal, were poised to fulfill their catastrophic purpose. A significant portion of these were not merely atomic, but hydrogen bombs. For those unfamiliar, a hydrogen bomb utilizes an atomic bomb as a trigger to ignite a far more destructive fusion reaction. "It felt like my head had turned into a computer," Petrov said, "a multitude of data, but they wouldn't form into a single, cohesive picture." No one can definitively say whether the leadership of the Soviet Union would have initiated a retaliatory strike had Lieutenant Colonel Petrov reported the attack. It was, undoubtedly, a highly probable scenario, for the geopolitical climate at that time was, to put it mildly, acutely tense. Nerves were frayed on all sides. It was the very peak of the Cold War. President Reagan of the United States had, by then, openly ceased to mince words, publicly labeling the USSR an evil empire and the focus of evil in the modern world. Furthermore, just 3 weeks prior to this incident, the Soviet leadership had issued a series of highly paranoid orders, leading to the destruction of a civilian airliner, Korean Airlines Flight 007, which was traveling from New York to Seoul. Due to pilot error, the airliner had strayed significantly off course and inadvertently entered Soviet airspace, where it was subsequently shot down by a Soviet interceptor. The tragedy resulted in the deaths of 269 people, including an American congressman, Larry McDonald. In essence, the situation was so volatile that both the United States and the Soviet Union were seriously considering options for launching preemptive nuclear strikes against each other, as each nation feared the other would strike first. The chances, by many estimates, hovered precariously at 50-50. Now, pause and truly consider the implications of this. The fate of the entire world, at that exact moment, hinged upon a microscopically small event. Whether a single calcium atom would land in a specific synapse within the prefrontal cortex of Lieutenant Colonel Petrov's brain. This precisely located calcium atom, if it struck its target, would trigger the excitation of a particular neuron, causing it to send an electrical signal. This signal, in turn, would initiate a cascade of activity in other neurons, collectively encoding the thought, "false alarm." "I picked up the phone," Petrov recounted, "and reported to the duty officer that the information coming from my command post was false. The computer had malfunctioned. All that remained was to wait and see if missiles, had they truly been launched, would invade Soviet airspace and be detected by other radar systems. This was expected to occur within 18 minutes. But it never happened. The world remained, miraculously, intact. For the 2 days following the profound shock he had endured, according to his son, Lieutenant Colonel Petrov simply slept, exhausted by the monumental burden he had carried. 6 months later, it would be determined that the malfunction had indeed been caused by an extremely rare phenomenon. The sun's rays, at a particular angle, had reflected off high-altitude clouds directly above the satellite, fooling its sensors. After the collapse of the Soviet Union, the world would learn of this incredible story. Stanislav Petrov would receive prestigious awards from German media for his contribution to the public good. At the United Nations headquarters in New York, he would be presented with a crystal statuette bearing the inscription, "The Man Who Prevented Nuclear War." Petrov would become a laureate of the Dresden Prize, awarded for preventing armed conflicts, and would even appear in a documentary film about those events, alongside the esteemed actor Kevin Costner. This is the history as we know it, the single linear narrative that unfolded in our reality. But there exists another reality, another story. The calcium atom that triggered the chain of events in Petrov's brain is a microscopic object, governed by the laws of quantum mechanics. As such, an atom can, quantum mechanically, exist in two slightly different positions simultaneously. And according to the many worlds interpretation of quantum mechanics, on that night of September 26th, the universe literally split into two distinct, parallel realities. Right now, in parallel with our own world, another exists. In that reality, the calcium atom did not land in the crucial synapse of Lieutenant Colonel Petrov's prefrontal cortex. Petrov, consequently, made the opposite decision. He reported the attack to his superiors, and a nuclear war commenced. One can only speculate as to what that alternate world looks like now, what ravaged landscapes and altered societies exist there. It is a kind of Schrödinger's cat experiment, but on the terrifying scale of an entire planet. The many worlds interpretation of quantum mechanics proposed by Hugh Everett III hardly needs an introduction. Much has been discussed about it, and over the past decades, many physicists have transitioned from either ignoring it or treating it with dismissive derision to seriously considering the possibility of an infinite splitting of the universe. Tegmark himself cites an informal survey of physicists conducted in 1997, which, while not claiming to be fully representative, was nonetheless indicative. In that poll, the majority of those who expressed a definitive opinion voted for the classical Copenhagen interpretation of quantum mechanics, which does not, embrace parallel universes. However, a similar poll conducted in 2010, this time at Harvard, yielded a dramatically different result. Not a single person voted for the Copenhagen interpretation. The absolute majority, instead, considered Everett's many worlds interpretation to be correct. The renowned ethologist Konrad Lorenz famously posited that important scientific discoveries typically pass through three distinct phases. First, they are ignored. Then, they are fiercely attacked. And finally, they are dismissed as self-evident. Judging by these survey data, Everett's parallel universes, having passed through the first phase in the 1960s, now seem to be situated somewhere between the second and third phases of this progression. Max Tegmark believes this shift is not just an academic trend, but a recognition of a profound truth. Many people express bewilderment, asking, "How can it be that I am constantly splitting into copies of myself, and yet I don't notice it? And how do I always feel like the same person?" To truly grasp this concept, and perhaps even come to terms with it, we must engage in a thought experiment. There is no known law of physics that explicitly forbids the creation of a complete copy of yourself, replete with all your memories, your personality, your entire consciousness. Imagine, then, that you fall into a deep, profound sleep. While you are unconscious, you are cloned using advanced super technology of the distant future. Upon awakening, if you are not told which of you is the clone and which is the original, you would never be able to definitively ascertain that you are, in fact, the original. For both of you, your past would be identical, and you would both experience the sensation of having lived a long, singular life, even though one of you came into existence only yesterday. In the realm of quantum mechanics, objects can exist in multiple places simultaneously, and their state is therefore described by a quote 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 way pastor. In simpler terms, a wave function is a mathematical description of the probability or degree of presence of an object in various locations. The many worlds interpretation asserts that the distinction between the micro-world and the macro-world is an arbitrary, contradictory, and somewhat fabricated construct. Therefore, the wave function must be used to describe not only subatomic particles but the entire universe itself. This means that the entire universe is described by a single, unified wave function. To put it even more simply, if the wave function allows a particle to travel along all possible trajectories simultaneously, then the entire universe in its totality does the very same thing. Thus, according to the many worlds interpretation, virtually any version of history that can be imagined, provided it does not violate the fundamental laws of physics, is just as real as our own. This concept might sound unfalsifiable, beyond the reach of empirical proof. However, it is possible that you, the listener, might one day provide evidence for it, because one of the probable consequences of the many worlds interpretation is your personal immortality. I discussed this in slightly more detail in a previous exploration titled Why the Universe Exists. But in brief, imagine yourself as an extremely old person, having surpassed the average lifespan in your country by many years. With each passing day, the probability of living another day would progressively diminish. However, and this is the crucial point, this probability can never reach absolute zero. Therefore, there will always exist universes in which you continue to live. And since it is impossible to subjectively experience non-existence, you will, from your own perspective, live forever. Of course, this particular consequence of the many worlds interpretation is met with considerable skepticism by many, as it involves numerous complex nuances. However, if, by some extraordinary turn of events, you one day find yourself, like Maria Brañas Morera, recognized as the oldest living person on the planet, then you might just remember the old Everett. Tegmark himself holds a strong conviction on this matter. His work in general remains contentious. However, I believe that he will one day be recognized as a genius equal to Newton and Einstein, at least in the majority of parallel universes. The ensemble of quantum parallel universes revealed by Everett, according to Tegmark, constitutes the third-level multiverse. As we observe, the third-level multiverse bears a striking resemblance to the first-level multiverse. However, while the universes of the first and second levels are situated within our familiar three-dimensional space, albeit at unimaginably vast distances, where then is the third-level multiverse located? It is, astonishingly, right here. The parallel universes of the third level are simply separated from us by an infinitely dimensional realm known as Hilbert space. Within this abstract, mathematical space resides the universal wave function that describes the entirety of the third-level multiverse. But what exactly paratsys this Hilbert space? What, for that matter, is this wave function? We clearly perceive that they constitute the very bedrock, the fundamental foundation of physical reality. So, what are they composed of? Tegmark's startling answer: nothing. They are purely mathematical objects. Did you truly hear what you just heard? The Nobel laureate in physics, Frank Wilczek, in his thought-provoking essay for the online publication Trog Quanta magazine, writes, "In my scientific career, I have had many diverse experiences, including some that led me into unusual states of consciousness. But I have had only one experience that could be classified as mystical." He continues, "I was alone there, inside a metal box the size of an aircraft hangar, looking down at the equipment people use to experimentally study the foundations of nature. And then it happened. Intuitively, it occurred to me that the complex calculations I had performed with pen and paper could somehow describe this completely different realm of existence, namely, the physical world of particles, tracks, and electrons created by the mechanism I was observing." Wilczek concludes, his words imbued with wonder. There was no need to choose, as philosophers often do, between mind or matter. They were mind and matter. How could this be? Why should this be? And yet I somehow, suddenly understood that it could and should be. The miraculous mystery of the correspondence between mathematical language and the laws of physics is a wondrous gift we cannot comprehend, and which we perhaps do not deserve. This brings us to the multiverse of the fourth level. In our previous discussion, we thoroughly explored why what a human directly perceives through their sensory organs cannot be considered objective reality. There, I primarily highlighted the rather radical viewpoint of the cognitive psychologist Donald Hoffman, who argues that our perceptions are merely icons or user interfaces designed for survival, not for truth. Whether he is entirely correct, I cannot say definitively. My aim, as the narrator, is primarily to illuminate diverse and interesting perspectives. However, what almost no one would dispute is that our perceived picture of the world is profoundly subjective. We only ever see a highly distorted, actively constructed model of reality, a product of our own brain. This is remarkably easy to demonstrate. How, in your opinion, does your perceived picture of the world change depending on whether you are moving your eyes or moving your head? From the perspective of the visual input, in both instances, you are simply shifting your angle of view. How could this possibly alter your perceived reality? It seems absurd, a foolish notion. Ah, but it is not so. Try it for yourself. Simply look straight ahead, and without moving your head, move your eyes from side to side. Then do the opposite. Keep your eyes fixed and turn your head from side to side. You may not have consciously noticed it before, but when you move your eyes, the space around you appears fixed, motionless. However, when you move your head, the world itself seems to move and no longer appears static. This same effect can even be achieved by simply closing one eye and gently, cautiously, rotating your open eye with a finger from side to side. You will again observe that the world appears to be in motion as if you were turning your head. This occurs because when you command your eyes to move via the eye muscles, your brain generates one kind of visual image, but it generates a asterisk different image if you command your eyes to move indirectly through the contraction of your neck muscles or by external manipulation with your finger. This phenomenon arises because the signals to these different sets of muscles originate from distinct areas of the brain. The detailed mechanism behind this was meticulously described by the 19th century physicist and ophthalmologist Hermann von Helmholtz. I will simply summarize by stating that this happens because you are not perceiving reality directly, but rather a asterisk model of reality projected and constructed by your brain. This internal model of the world is your internal reality. What the external reality truly looks like, beyond the filters of our sensory organs, remains a profound and open question. We are intrinsically confined within our own bodies. We cannot step out and directly observe what the universe is really like. Our internal reality tells us only what our ancestors needed to know for survival, nothing more. However, we have, to our astonishment, discovered that we do possess a pathway to external reality after all. A very strange pathway indeed. Have you grasped which one? It is through mathematics. Your direct perception tells you that you are gazing at a solid, motionless stone. But the mathematical description of that stone reveals a vastly different truth. In reality, with the exception of a quadrillionth of its volume, the stone is almost entirely empty space, composed of particles, undergoing constant, vigorous vibrations. And we believed, nice to mathematical description, we trusted even more than our subjective sensory perceptions, because if we did not, we would never have constructed our modern civilization with its incredible, mind-boggling technologies. Why does external reality lend itself so perfectly to mathematical description? No one truly knows. This question has tormented humanity for several millennia, and today, this question is more urgent and perplexing than ever before in human history. While preparing the material for this monologue, I visited numerous forums and online discussions. At times, people were almost willing to physically fight each other, fiercely defending one side or the other of this enduring debate. And the question itself is simple, yet profoundly divisive. Is mathematics an invention or a discovery? In other words, can we genuinely assert that mathematics exists independently of the human mind? Can we say that we merely discover mathematical truths, much as explorers once discovered new islands and continents? Or is mathematics nothing more than a human invention, a sophisticated tool created by our intellect? If it seems to you that knowing whether we invented or discovered mathematics is not particularly important, I urge you to consider how heavily laden the difference between the words invented and discovered truly is. To rephrase the question in a more provocative way, as Mario Livio suggests, what about God? Did we invent him or discover him? Or even more provocatively, did God create humans in his own image? Or did humans invent God in their own image? One might also ask, what does it even mean for mathematics to exist independently of the human mind? Are numbers literally floating around in reality? The issue is not about the digits themselves or other mathematical symbols. We can, of course, invent any symbols we choose. The real question lies in what stands behind these symbols, and behind them stands something profoundly suspicious. These suspicions, I reiterate, first emerged several thousands of years ago, but Isaac Newton's groundbreaking work truly blew everyone's minds. He demonstrated that the same mathematical laws governing an apple's fall on Earth also precisely described the motion of the moon around the Earth, or the Earth around the sun, only on a vastly larger scale. It suddenly became clear that mathematical laws manifest not just locally, on Earth, within the human world, but also across cosmic scales. As the English physicist James Jeans once famously remarked, the universe appears to have been designed by a pure mathematician. And the astrophysicist Mario Livio, in his book Is God a Mathematician, writes, "Concepts and relationships that mathematicians study for pure science, without even considering their practical application, unexpectedly, sometimes decades or even centuries later, turn out to be solutions to problems rooted in physical reality." And this, as you've already heard today in the stories of Feigenbaum, Ramanujan, and Hardy, is not a collection of isolated incidents. There are countless such examples. New types of geometry, for instance, first described by Georg Riemann in his classic lecture delivered in 1854, proved to be of paramount importance to Einstein. It was precisely these geometries that allowed him to mathematically describe the very fabric of spacetime, the weave of the cosmos. The mathematical language known as group theory, developed by the young genius Évariste Galois solely for the purpose of determining whether certain algebraic equations possessed integer roots, has today become the indispensable language of physicists, engineers, linguists, and even anthropologists, as Mario Livio pointsifies. The planet Neptune, for another striking example, was discovered only now after its existence was predicted on paper through intricate mathematical calculations. Complex numbers were proposed centuries before physicists began to use them to describe the bizarre realm of quantum mechanics. Non-Euclidean geometry, which challenges our everyday assumptions about space, was conceived decades before Einstein's theory of relativity. Albert Einstein himself, reflecting on this profound puzzle, once wrote, "How can it be that mathematics, being after all a product of human thought independent of experience, is so admirably adapted to the objects of reality? Could it be, then, that the human mind, through the sheer power of thought, without recourse to experiment, can grasp the inherent properties of the universe?" Such astonishing effectiveness of mathematics has, in a very real sense, turned the entire scientific method on its head. Whereas scientists once primarily gathered experimental data and only then attempted to describe it using mathematics, today the process is often precisely the reverse. Mathematical models are constructed first, and only then are experiments devised to test their predictions. And even this is not the full extent of the shift. Some contemporary scientists, including truly towering figures like Roger Penrose, argue that experiments are not even strictly necessary. They contend that the mathematical models themselves are entirely sufficient to qualify a theory as scientific. And after everything we have explored today, after all the profound insights and bewildering coincidences, can we truly blame them for this perspective? The situation has, in fact, reached its apex with the emergence of equations that work flawlessly, but which we struggle to reconcile with the reality we directly perceive. That is to say, the two foundational theories upon which our entire modern civilization is literally built, the theory of relativity and quantum mechanics, speak of reality in ways that can only be described as schizophrenic. The theory of relativity declares that the flow of time, as we intuitively experience it, does not fundamentally exist, and that there is no singular present moment. Quantum mechanics, on the other hand, well, what does it truly say? It is so profoundly perplexing that, since the mid-20th century, dozens of interpretations have proliferated, each attempting to make sense of its bizarre implications. However, I reiterate, the equations themselves work impeccably. Modern physics, in describing the external world, relies almost entirely on mathematics alone. So what then does this external world truly represent? In Douglas Adams' famous satirical novel, The Hitchhiker's Guide to the Galaxy, a supercomputer named Deep Thought is tasked with finding the answer to the ultimate question of life, the universe, and everything. After 7.5 million years of complex calculations and rigorous cross-verification, the computer finally delivers its succinct answer: 42. 42? Is that all you can tell us after 7.5 million years of work? The eagerly awaiting beings exclaim. I've checked it thoroughly, the computer replies, and I can state with all certainty that this is the answer. Max Tegmark, with his characteristic blend of humor and intellectual depth, considers this answer to be remarkably apt. Do you recall the scathing letter Tegmark received at the beginning of our journey today, the one that the angry professor warned could bury his career? In that very article, the one that provoked such a sharp reaction, Tegmark proposed the audacious idea that our entire physical world hinders a giant mathematical object. He argues that the problem of the, quote, unreasonable effectiveness of mathematics only arises when we perceive mathematics and physics as two separate, independent disciplines. But if we hypothesize that they are, in fact, one and the same, everything instantly falls into place. If two structures are equivalent, Tegmark posits, then there is no meaningful context in which they are not one and the same. If certain mathematical equations describe both our external physical reality and a mathematical structure, then our external physical reality and that mathematical structure are one and the same. This belief, that mathematical objects exist in reality, that they are perhaps even more real than what we directly observe with our eyes, dates back to Plato and is known as Platonism. And, as Tegmark asserts, if his journey in physics has taught him anything, it is that Plato was right. But how can physical reality and mathematics truly be one and the same? How can mathematical objects exist in reality? Where are they? I do not perceive any equations floating around me. Let us revisit our example of the stone. Yes, it is, as we established, primarily empty space between minuscule particles that occupy almost no volume. However, can we truly say that these particles themselves are abstract? Indeed, we can. Quantum mechanics posits that subatomic particles are not merely tiny solid spheres. Instead, they are best understood as nothing more than concentrations of mathematical properties. The very fabric of our physical world, its space, is itself a purely mathematical object, in the sense that all of space's inherent properties, its number of dimensions, its curvature, its topology, are fundamentally mathematical. The filling or content of our physical world consists of fundamental particles, which in turn are purely mathematical objects in the sense that all their inherent properties, for example charge, spin, lepton number, and mass, are mathematical. Even more fundamentally than our three-dimensional space with particles within it is the wave function and the infinite-dimensional Hilbert space in which it resides. Both the wave function and Hilbert space are purely mathematical objects. Max Tegmark states this directly. This leads us to the final type of parallel universes, the fourth-level multiverse, a realm so vast and exotic that it dwarfs all others. The fourth-level multiverse encompasses completely unrelated realities, each corresponding to distinct fundamental laws of physics and governed by entirely different mathematical equations. But if, at the very deepest level, reality is a mathematical structure, then what are its constituent parts made of? The answer, startlingly, is nothing. Mathematical structures have no intrinsic properties in the conventional sense. The properties of our surrounding world are determined not by the inherent properties of these mathematical blocks, but by the asterisk relationships between these blocks. To illustrate this roughly, a table is a table not because each of its individual components possesses an intrinsic tableness, but because these components are organized in a specific, functional way. A table is, in this sense, something greater than the sum of its parts. However, a crucial distinction between the fundamental blocks from which the universe is constructed and the materials of a table is this. The material from which a table is made, be it wood or iron, still possesses its own inherent properties. It is wooden or iron. But the primary blocks that constitute the universe possess no inherent properties whatsoever. Therefore, nothing meaningful can be said about them directly. One can only speak meaningfully in terms of the relationships between these blocks, but not about the blocks themselves. If you find this concept difficult to imagine, to truly grasp, you are not alone. I have delved into various sources, and this is what I found. Roger Penrose, in his seminal book The Road to Reality, in a section aptly titled, Is Plato's Mathematical World Real?, writes, I appreciate that many readers will find it difficult to conceive of mathematical structures as endowed with any actual independent existence. To such readers, I want to address one simple request. Try to slightly expand the usual meaning of the word existence. He elaborates, of course, mathematical forms in Plato's world do not exist in quite the same way that ordinary physical objects, such as tables and chairs, exist in our world. They do not have a spatial location. They do not exist in time. Perhaps there is indeed much to ponder here. The most intriguing aspect is that if Tegmark is correct, despite its apparent complexity, the universe is, in fact, incredibly simple and contains almost no intrinsic information. Consider this beautiful mathematical structure, known as the Mandelbrot set. Within this structure, intricate patterns exist at arbitrarily small scales. And although many of them appear similar, no two are ever truly identical. The set can be magnified indefinitely, and thus, it seems infinitely complex. However, the entire Mandelbrot set is fully described by a single, deceptively simple formula, z squared plus c. This suggests that all the perceived complexity of the universe could be generated from similarly concise and elegant mathematical principles. It is reminiscent of how James Clerk Maxwell condensed 4 volumes of experimental results and descriptions in the fields of light and electromagnetism into just 4 simple, elegant formulas, which are now so iconic they appear on T-shirts. The profound question then becomes, how does humanity, how do we, fit into this grand mathematical picture of the world? Livio eloquently poses the question. The perceiving consciousness, the very dwelling place of conscious perception, is born in the physical world in ways we do not understand. But how exactly does matter give rise to consciousness? And how is it that we can somehow access these mathematical truths? Will we ever be able to formulate a theory of consciousness as unified and convincing as, for example, our current theory of electromagnetism? Here, the cycle of wonder exquisitely closes. The perceiving consciousness, through some enigmatic mechanism, possesses access to this mathematical world. For it is consciousness that either discovers or creates and articulates a vast treasury of abstract mathematical forms and concepts. And indeed, the precise connection between mathematics and our brains remains utterly unclear. We know, for instance, that ants and bees possess the ability to count. Certain species of spiders tally the number of insects caught in their webs. Animals, in general, can effortlessly add and subtract small numbers. Rhesus macaques and parrots can operate with numbers up to 6. Pigeons can, with surprising accuracy, solve subtraction problems like 12 minus 6. Lionesses estimate the number of individuals from another pride that have roared to decide whether to attack or retreat. Virtually all animal species that researchers have studied can distinguish quantities of objects in sets or sounds in sequences. Furthermore, experiments have demonstrated that monkeys, crows, and bees understand how to handle the concept of zero and can correctly place it on a numerical line. Experimentally, it has been proven that 5-month-old infants can solve basic arithmetic problems like 1 plus 1 and 2 to 1. And this innate ability develops in them even before their language skills emerge. It is evident that there is some form of evolutionary pressure at play here, and that, at the very least, rudimentary mathematical skills are inborn. There is an undeniable evolutionary aspect to our capacities for mathematics. But can the theory of evolution truly explain cases like the savant twins, or the genius of Ramanujan, or, more broadly, our human capacity for understanding mathematics that extends far beyond any natural applicability, any direct survival advantage? How can a brain shaped by the selective pressures of the African savanna be capable of such profound understanding of something utterly unrelated to that savanna, something as abstract as quantum field theory, or the geometry of higher dimensions? I remain profoundly bewildered as to why mathematical laws should necessarily describe the physical world with such phenomenal precision. And if it were merely a matter of accuracy, that would be one thing. But no, equally enigmatic are the refined complexity and the sheer mathematical beauty of our most successful scientific theories. It remains absolutely incomprehensible how, within physical matter organized in a particular way, here I refer to the living human or animal brain, the mental quality of meaningful awareness suddenly arises, seemingly out of nowhere. And finally, it is still unclear by what ingenious means a human assesses the truth of a mathematical statement. This mental quality cannot be explained solely by stating that our brain is somehow programmed for the correct execution of certain computations. There must be something else beyond mere calculation, something that allows even the most mathematically challenged among us to grasp the actual, intrinsic meaning of concepts such as 0, 1, 2, 3, 4, and so on. Roger Penrose emphasizes this enigma. So, what then are we, within the framework of Max Tegmark's mathematical universe hypothesis? We are, in essence, unchanging mathematical space-time patterns of the universe. Allow me to explain. From our conventional perspective, for example, the Earth and the Moon appear as they are now, two rocky spheres revolving around each other in the vastness of space. But from the perspective of Einstein's theory of relativity, they appear fundamentally different. Einstein's theory demonstrates that time is not merely an abstraction. Rather, every point in the past, present, and future exists in reality, in the most direct sense of the word. Therefore, the Earth and the Moon, conceptually omitting one spatial dimension for simplicity, actually appear like this. They create a single, unchanging, simple pattern within spacetime, a continuous, interwoven trajectory. The path of an object in four-dimensional spacetime is called its world line, and for almost all non-living objects, these world lines are relatively simple and uncomplicated. However, everything changes when we consider living objects. Even if you are simply sitting still at this moment, within you, complex biochemical reactions are constantly occurring. Blood cells circulate through your body. Neurons fire electrical impulses in your brain. All of this activity forms a structure in space-time that resembles a complex, intricately braided rope, but infinitely more elaborate. I have attempted to illustrate a few simplified examples. Imagine a depiction of two friends meeting, a brief convergence of their world lines, or the birth of a child to its parents, a new world line emerging from two others, and then the cessation of a world line, representing death. Of course, these are shown here as animated concepts, but I reiterate, from the perspective of the theory of relativity, these are absolutely static, eternal, and unchanging objects, just like everything else in the four-dimensional universe. As Tegmark writes, the human world line is undoubtedly the most complex of all patterns in our observable universe. For example, the space-time pattern of a single human being is vastly more intricate than the space-time pattern of an entire star, like our Sun. Complexity is a defining characteristic of life itself. But there is still more. Everett's quantum mechanics endows us with an even more intriguing structure. Since each of us, like the trunk of a tree, can conceptually split into a multitude of branches, which in turn split further and further, we form a beautiful, endlessly branching pattern within the infinite mathematical universe. As for consciousness itself, from Tegmark's perspective, consciousness is the way information feels when it is being processed by certain complex methods. He posits that it arises when a model of oneself within your brain interacts with a model of the world within the same brain, or indeed when the self-model interacts with itself. Roger Penrose, reflecting on the profound implications of these ideas, shares his personal contemplation. What feelings does the possibility stir in me that all my actions and those of my friends are ultimately governed by such mathematical principles? I believe I can bear it. I even think that for me it is preferable to believe that all these actions are governed by something existing in some objective sense in Plato's ideal mathematical world, rather than to allow myself to be convinced that human behavior is wholly and entirely determined by simplistic, unchanging motives like greed, aggressive cruelty, or the pursuit of pleasure. Such a worldview, many assure us, should be the sole outcome of applying a strictly scientific approach. Tegmark's mathematical universe hypothesis is, crucially, a fundamentally testable and falsifiable proposition. It could be disproven if physicists, even without a complete and comprehensive description of physical reality, were to cease discovering mathematical regularities within nature. The four levels of multiverses, as you might expect, certainly have their critics, who put forth strong arguments against them. You might encounter some of these counter-arguments in your own explorations. And yet this is Max Tegmark's response to such criticism. As strange as it may seem, I agree with all 7 of these assertions. And, nevertheless, I would gladly bet all my savings on the existence of the multiverse. And, it is quite difficult not to respect a person who is unafraid to express such radical ideas so openly, especially within the often conservative and somewhat snobbish scientific community. Whether Tegmark is ultimately right or wrong, mathematics truly remains a profound mystery, one that we may yet only be beginning to unravel. In creating this monologue, I drew upon a variety of sources, most notably Max Tegmark's illuminating book, Our Mathematical Universe, and Mario Livio's thought-provoking work, Is God a Mathematician? Both come with my highest recommendation for anyone seeking to delve deeper into these fascinating concepts. Consider, for a moment, the concept of magic across the histories of diverse cultures. Magic is often depicted as an incredibly intricate system of knowledge, one that practitioners often devoted their entire lives to mastering. Magic is inherently mysterious and is believed to bestow superhuman abilities upon those who truly comprehend its secrets. Adherents of magic believe that beneath the surface of the reality we commonly observe lies a hidden or occult level of existence, and that they, as possessors of specialized knowledge, can penetrate this hidden level and bend the world to their will. Magic, to many, seems like the antithesis, the complete opposite of science. But now, consider this. If you were to replace the word magic with the word mathematics in that preceding description, would its ultimate meaning fundamentally change? And perhaps, in our childhood mathematics lessons, we would all have been a little more engaged, a little more captivated, if we had been told that the subject was only called mathematics in our particular universe. And even then, perhaps due to some silly mistake. For truly, in our modern world, asking why is mathematics needed is akin to asking, in the world of Harry Potter, why is magic needed?